Okay, now I'm going to verify this formula, not this one. We could verify either because there's a very close connection here. Just divide through by m. Taking the form x equals a cosine omega t plus phi, one of the three forms of the position function, we easily take a derivative to calculate the velocity function. And of course the chain rule gives us an omega out here. Derivative of cosine is negative sine. And then another derivative, we get another omega from the chain rule, and we get our acceleration function. And it's kind of worth noting that this part of the function is the same as this. Okay? In other words, this is equal to this, which is x. So that the acceleration is negative omega squared times x. Another really kind of handy thing to know that just pops right out once you do a few simple derivatives. Okay? Now, to verify, we want to verify using the equations of motion that this equation holds. So what do? Well, the obvious thing to do is we got an expression for v, plug it in. We get this. We got an expression for x, okay, plug this in for x. That's what we have. And we get this equation. I'm not going to read it to you. You can check. I think everything is there. And I doubly think so because everything does work out. Okay, so now we want to simplify this. We square this term. We get our omega squared, a squared, sine squared, and so forth. We haven't, and we square this term, we get an a squared and a cosine squared. And the argument omega t plus phi, both on the sine squared and the cosine squared. I don't have to read that to you. You understand it, and you can certainly see that if we just square these terms, this is what we get. Okay? Now, we come over here because we've got like this m omega squared a squared. Okay? Now, this is the only place we have an omega outside of the argument of the sine or cosine. And we have to remind ourselves what omega means at this point. Okay? Omega, in the solution of this equation, omega stands for the square root of k over m. Again, solve this equation, know how to solve this equation, you see right where omega comes from. So that this m omega squared a squared becomes m, and it's a little jumbled here, but I've replaced omega with the square root of k over m, and it's that squared times a squared. And if you square the square root of k over m, you get k over m, and if you multiply that by m, you get k, so this is just k a squared. So now this term becomes 1/2 k a squared, and that takes care of the omega squared and the a squared, so times the sine squared of omega t plus phi. I just wrote parentheses here to save a little space. Okay? And then we add this term to both sides. And of course this term is 1/2 k a squared cosine squared omega t plus phi. Adding it to both sides, we get plus 1/2 k a squared times the cosine squared of omega t plus phi. Same argument in the cosine as the sine, and same coefficient, 1/2 k a squared, so we factor out 1/2 k a squared. It leaves us sine squared of omega t plus phi plus cosine squared of same thing, omega t plus phi, and the sine squared plus the cosine squared of the same argument is 1, so the left-hand side just becomes k a squared, and that's equal to the right-hand side, 1/2 k a squared, not k a squared. Okay, both sides come out 1/2 k a squared, so we just say, once we see this, we should have an aha moment. This all works out. This identity is validated by the equations of motion, giving us a really good feeling for the consistency of this whole picture. Now, I really do recommend that you be able to develop this whole picture when you come into the final and at any point in your subsequent life. It's a fairly simple, but not trivial, okay? It's an accomplishment to pull all this together. I'm not denigrating that. I'm not saying that it's not a really good thing. On the level of the difficult and challenging concepts you're going to have to deal with in your future education. This one is reasonably accessible, okay? So, starting from F net equals negative kx, we get the expression for the potential energy, and we get a differential equation that we don't even have to use techniques of differential equations for. There are existence theorems and other theorems that tell you, yeah, you really do get two arbitrary constants, stuff like that. But you don't need those. This is not a difficult thing to solve. Okay? What has a second derivative that's a multiple of itself? A sine, a cosine, or an exponential. Okay? And that's it. And in this case, the exponential doesn't work. The sine and cosine do, so there you are. And the work integral is really easy to do. You don't even really need an integration. You just do it by a graph because it's a linear function. Multiply the average value by the change in x, and this is what you get. Okay? Now, I haven't said that very specifically, but we've seen it previously more than once. Okay, so fairly simple picture. Ask yourself the question, what's the total energy? What's the velocity at a point? You're going to be led to, well, what's the kinetic energy at a point? Total energy minus potential energy. We know the potential energy at every point, so we know the total potential energy at the point, subtract them. You get the kinetic energy, solve for V. Plug the velocity and acceleration functions that come out of this solution into that, and you get an identity. If you have that picture, you're going to have a pretty powerful set of tools with which to show off when you do your analysis of simple harmonic motion.